Thank you for the introduction. The title's different from the advertised one, but the content's the same. There's two questions. If I have my glasses, I can read them. The first question is, will artificial intelligence soon be smarter than us? And for a long time, for like 50 years, I was working on trying to make artificial neural nets in order to understand how the real brain might work. And I always assumed that the real brain was better and the artificial neural nets were worse. And if you made them more like the brain, they worked better. And a few months ago, I suddenly changed my mind. And that's why I decided to leave Google and talk about the risks. And the risks, obviously, will people be able to stay in control if you get super intelligent things? Because there's no examples of a more intelligent thing being controlled by a less intelligent thing since Biden won the election. I'm going to make a few speculations about that, but the main content of the talk is just going to be about the reason why I think these things are going to get more intelligent than us. So the first question. I don't know much about risk. I talked to a whole bunch of risk people today who knew much more than me, so I won't talk about that. So in conventional computing, you use computers that are designed to follow instructions. And the fundamental property of a computer is that you can run the same program on different pieces of hardware. And so the knowledge in the program is immortal in the sense that if a piece of hardware dies, the knowledge doesn't die. You can run it on another piece of hardware. To do that, you need to run transistors at very high power so they behave in a reliable digital way. And you can't make use of the analog properties, the analog and highly variable properties of a particular piece of hardware, because then you wouldn't be able to do the same thing on a different piece of hardware. So I got interested because of the very high power used by these large language models, the big energy consumption. I got interested in whether there was a much cheaper way to do computation in terms of power that we could use now and we couldn't use previously. And digital computers were designed to be programmed by people, which is why they had to follow instructions precisely. But now we know a different way to make general purpose computers do particular tasks, which is learn from examples. And if they learn from examples, maybe we can get rid of this basic principle of computer science, which is you have to separate the software from the hardware. Maybe we can use analog computers that make use of all these analog properties and aren't reproducible. So you just can't transfer the knowledge to another computer, but you can run at very low power, like 30 watts. So obviously there's big advantages to separating software from hardware. You can write one program and it'll run on all your iPhones. It also means you can have a separate department where you don't know anything about electrical engineering and you call yourself computer science. If it's all mixed up together, you can't do that. And so when you don't separate the software from the hardware, you get what I call mortal computation. That is, you're going to learn in the hardware, and what you learn is only going to be any good for that particular piece of hardware because you're making use of all its weird analog properties. Now that's great because we can use low power analog computation, and we can maybe grow hardware in 3D where we don't know the connectivity or the precise properties of the individual neurons, if it's neural net-like hardware. But we've obviously got one big problem, which is we're going to have a learning procedure that can learn in this hardware without knowing the exact properties of the hardware. And I'll talk a bit about how you might do that. It's probably not going to be backpropagation, because in backpropagation, you have a forward pass through layers or through time, and you have to know the properties of the forward pass in order to use backpropagation to get gradients. If you don't actually know the properties of the hardware, you need a different kind of learning algorithm. So advantages of mortal computation, you can use weight level parallelism. So you can have trillion-way parallelism. And that means your computing elements don't need to be very fast. That's what the brain does. And we can use hugely less energy, and we can grow the hardware. Now, it might be good not to start again from scratch. I was guessing that we would end up actually re-engineering biological neurons as the hardware. but as you'll see, we may not have time for that. So I just want to give you one example of a computation that's obviously much more sensibly done analog than digital. So suppose you want to multiply a vector of neural activities by a matrix of weights. And that's what we want to do all the time. That's the main computation we do. So you could drive transistors at very high power and represent the activities as digital numbers, and then perform a whole bunch of operations on the bits to multiply them together. Or you could make the neural activities just be voltages, and you can make the weights be conductances. And there's physicists around, so I hope I got the units right. If you multiply voltage by a conductance, I think you get a charge per unit time. And charges add themselves up. So now you can multiply a vector by a matrix very simply without ever representing anything digitally. And it's very efficient. There are chips around that do that now. The problem they have is then they try and digitize things afterwards before they do anything else with it. But this particular computation can be done efficiently. So the other big, I'll get back to the learning problem in a minute. The other big problem for mortal computation is that hardware dies and then everything it knows gets lost. And so the solution to that problem in mortal computation, there's a completely different solution in digital computation, but in mortal computation, the solution is the teacher tries to distill the knowledge into a student. And the way you do that is the teacher shows the student the correct responses to some input, and the student tries to mimic those responses. And that's what was going on with Trump's tweets. Left-wing people kept complaining that all the things he said were false. That was completely irrelevant. That wasn't the point. The point was you take a situation and you show people how to react to it, and your followers try and react like that. And it turns out that's much more effective than reasoning with people. So that's how distillation works for distilling prejudice. So let's think about an agent that's classifying images into 1,024 categories. If you just tell the agent the right answer, you're only giving them 10 bits of information. So you're only constraining the weights by 10 bits when you say you should give this class for this input. But suppose you already had a teacher who was trained. The teacher will give probabilities for all the outputs. And that's 1,023 real numbers because they add up to 1. And as long as those probabilities aren't too small, if you train a student to mimic a teacher, each training example is far more valuable because the student is trying not just to get the right answer be the most probable thing, assuming the teacher got it right. The student's trying to match the probabilities of the teacher for all the other training examples. And actually, in many cases, there's much more information in the relative probabilities of wrong answers than there is in the right answer. So for example, if I show you a BMW, the system will say sort of 0.8 is a BMW and 0.1 it's an Audi, and there's a 1 in a million chance that it's a garbage truck. There's no German manufacturers here, no. There's 1 in a million chance it's a garbage truck, but the point is, it'll also say there's a 1 in a billion chance that it's a carrot. And if you look at all the things that get a 1 in a million chance, they're other vehicles. So it's telling you a lot about the classes of things by all the things that get low but not totally zero probabilities. And vegetables is not, and so they get very much smaller probabilities. And that ratio between the garbage truck and the carrot is telling you a whole lot. So training a student to mimic the probabilities of a teacher is good, especially if the probabilities aren't too small. And we can make the probabilities not too small by using a high temperature. So normally, if you have multiple alternative outputs, you use the Softmax, which is, you say, the probability of each answer is proportional to e to the logit for that answer, where the logit is the amount of evidence you got for that answer. If you just scale that by temperature, you get much softer probabilities. And so I've got an example of that where it may surprise some of you to know I use the MNIST digits. And I've got a good teacher, and then I've scaled down the probabilities so they're much softer. And if you look at this, these are all 2s. But if you look at that middle row, the teacher thought, yes, it's a 2, but it's just slightly like a 0. It's much more like a 0 than any of the other 2s. And so you can see on that one training example, you're teaching the system things about zeros as well by saying this is a 2 that looks a bit like a 0. Or if you look at the second row, that's a 2 that looks a bit like an 8. And that's very useful extra information. So the reason I'm talking about distillation quite a lot is because that's how we get knowledge between ourselves. It's also how you get knowledge between one digital system and a different neural network that's got a completely different architecture. So often you want to train a great big model and then get that knowledge into a smaller model, and you use distillation for that. And one nice thing about distillation is when you're training the student from a teacher and training the student to get the same probabilities for wrong answers as the teacher, you're actually training the student to generalize the same way as the teacher. So it's one of the very rare cases where you're actually training the student on how to generalize. Normally you just train it to get the right answer and hope it'll get the right answer in other cases. But here we're actually training it to generalize. And obviously a single label isn't a very rich answer. So you'd be better off training the student by giving it an image and then giving it a great long caption for the image and training it to predict all the words in the caption. And that way you can get more information per training case. So that makes distillation work better. So that's how distillation is, how you get information between two analog systems. And that's what we were doing then. You've got a very old analog system here, and you've got a few old ones and a lot of young analog systems there. And we're trying to get information from this old analog system into these young analog systems. And the whole point of this talk is that process isn't very efficient, as I just demonstrated. It's a slow and painful process. We can't get, wouldn't it be great if I could just sort of go chunk and everything I knew went into your brain? That would be so good. Wouldn't be much good for the university, but it would be, yeah. But that's what biological systems have to do. Now let's talk a bit about the learning algorithm, because this is what, thinking about this was one of the things that made me change my mind about which is better, digital systems or biological systems. So if you don't want to backpropagate because you don't actually know what the hardware is doing, you can use a simple algorithm which is got an evolutionary flavor, which is you generate a small random perturbation to the weights, and you have some global objective function. You put some examples through, and you see whether you do better or worse on this objective function after you've made the perturbation, and then you take a step in the direction of the perturbation that's proportional to how much better you did. And the thing about that is, on average, it's going in the right direction. If you do it enough times, you'll go in the same direction as backpropagation, but it's got very high variance. So it'll only work in very small systems. Also, if you use the same weight perturbation for everything in a mini batch of examples, you get even worse variance. And if you use different weight perturbations, you can't use matrix multiplies, but that's just for insiders. It's much better to use activity perturbation, where you perturb the input to a neuron, and you do the same thing. We perturb the inputs to all the neurons, so they get the inputs they're getting from the rest of the net, plus this additional perturbation. And then you see how much better you get as a result of that perturbation, and take a step in that direction proportional to how much better you got. And obviously, there's far fewer neurons than there are weights, so it's got much less variance. And that's good enough to learn problems like MNIST. It learns slower than backpropagation, but it learns at a reasonable speed. The problem is, once you start trying to scale that to big nets, it's just hopeless. You can learn things like MNIST, you can learn things like CFAR10 if you're very determined, but ImageNet, where you have millions of images or 1 million images, is just much too slow. So one way around it that avoids doing global backpropagation is to say what we're going to do is we're going to actually have gazillions of local objective functions. So the way we're going to scale things, you naturally think, I get a little neural net, it works. I have a little neural net with this objective function. I can train it, that's fine. What if I want a big neural net? You try the same training algorithm, it doesn't work. But what if I had lots of little neural nets, each with its own objective function? And in vision, they could all be spatially local. I give it its own objective function, so I'm never trying to learn lots of parameters all at once from one objective function. And that works. It doesn't work as well as backpropagation, but it does scale up much better to larger nets made of lots of local groups. So the question is, where do you get these local objective functions? And here's one possibility for vision. You take patches of image, and you have a little net that extracts something, a vector that's going to represent what's going on in the patch of image. And you say, I'd like to extract vectors that agree with the vectors extracted by other patches for this same image, but disagree with the vectors extracted for other images. So this is called contrastive unsupervised learning. And it turns out you can do that in multiple levels. So you're doing learning on local patches, trying to get them to agree with other local patches at the same level, trying to get the outputs to agree. You're also doing that at multiple levels. And if you're very persistent, you can make that work moderately well. It works better than all the other biologically plausible learning algorithms I know about. It still doesn't work nearly as well as backpropagation, though. And there's a paper about that in ICLR by Meng-Yi Ren, who did all the difficult work. The description I gave of it is slightly false, so you could understand it easier. But the paper's there, so I don't feel it's dishonest. It took a lot of hard work, and it's a fairly dense paper. Okay, now let's go to the central issue of this talk is how agents share knowledge. It's all about communication between different agents. So what I'm doing now is trying to communicate knowledge to you, and I'm doing it very inefficiently. And the way I'm doing it is I'm producing strings of words. In old-fashioned AI, what you would have done is said, what's going on is you're then going to clean up those words into a logically unambiguous language, and you're going to put them in your brain. And that's what teaching is. That's actually wrong. That's not how it works. How it really works, I believe, is this. I produce strings of words, and you try and figure out how to change the connection strengths in your brain so that you would have said that. And that's a very different process. That's distillation. That's a very different process from just storing strings of words or storing even cleaned up strings of words. You're trying to figure out how to change trillions of weights in your brain so that that will be a reasonable thing to say. That is, if you believe me. So that's a difficult way to share knowledge, and digital computers have a much better way to share knowledge. So they can do weight or gradient sharing. So suppose I have a big artificial neural net with 1 trillion connections. If I have it on a digital computer, I can make exact copies of it on lots of different digital computers. And each copy can go off and look at a different bit of the internet and figure out how it would change its weight so that it would have said that. And then it can take that weight change that it would like to make, and it can talk to all the other computers, and they can all agree to average all their weight changes. This is a simplification, but if you know, yeah, it's a simplification, but it's basically that. They average all their weight changes, and then everybody knows what each digital computer learned. So basically, it's what educators would love, which is I can take what's in my brain and can just plonk it in your brain. The hell with all this trying to predict what I would say. I just want to take what's in my brain and put it in your brain. And these digital intelligences can do that. And they do it by they all agree on the weight change, and now they all know what all of them learned. So imagine if we had 10,000 people, and whenever one of us learned something, all of us knew it. That would give you a tremendous advantage. And that's the advantage that digital computation has. In addition, it's got the advantage that it can use backpropagation, which is probably a better learning algorithm, because that can go through lots and lots of layers of neurons and compute exactly the correct gradient None of this guess a direction and see how well it works and hope you can average away the variance. It's a better learning algorithm. So all of this came as a tremendous relief to me, because I spent the last few years trying to come up with biologically plausible learning algorithms that work as well as backpropagation. And I finally decided maybe there aren't any, maybe backpropagation is actually better. And that's what I think I now believe. So I just want to remind you that you pay a tremendous cost to get this. And the cost you pay is that they have to be digital computers, they have to be fabricated precisely so they do exactly what they're told to do at the level of the instructions, and it uses a lot of energy. Distillation is what we use if we've got biological neural networks, or if you've got two digital networks that have completely different architectures. But it's got a much lower bandwidth. So if you've got a digital model with 1 trillion connections, they all go off and look at some data, then they average their weights. When they're averaging their weight changes, that's trillions of bits that are being communicated. When you try and predict a sentence that I say, when you try and change your weights so you predict the sentence, that's hundreds of bits at best. If you're Carl, it's about 2 bits, because he knew what I was going to say anyway. So it's much lower bandwidth. So here's the story so far. There's 2 very distinct ways to do computation. And the primary way in which they differ is in how you communicate knowledge between different agents. So in digital computation, you use weight sharing. And you've got this tremendous bandwidth for sharing what each agent learned. In biological computation, you can use very low power if you make use of the analog properties of the hardware. But now sharing knowledge is a slow and painful business. So now let's look at large language models, because every AI talk now has to get to large language models eventually. They're quite interesting. They use digital computation, so you have lots of different copies of the same set of weights running on different computers when it's learning, and they all look at different bits of the internet. And that allows them to see a huge amount of data and consolidate all that knowledge, because they can share what they learn. And so if you look at large language models, they have about 1 trillion weights, and they know probably 1,000 times as much as any one of us. They kind of know everything. GPT-4 sort of knows every plausible thing, every reasonable thing it knows. Now we have 100 trillion connections, so we've got 100 times as many connections. So we're really not using all that power, but it's because we can't see enough data. And if only we could get the knowledge from other people, maybe we could use it all. But they've got 1,000 times more knowledge in 1% of the connections, which sort of confirms the argument they've got a better learning algorithm. The combination of backpropagation with this easy communication between different agents with the same weights means they basically got a much better learning algorithm. Now, it's presently being used to steal all our knowledge. Sorry, steal's not the right word, particularly in the current political context. It's to acquire our knowledge by using distillation. So these digital agents that can share knowledge, each agent, when it tries to get knowledge from the web, is using distillation to get the knowledge. It's looking at what people said and trying to change its weight so it would have said the same thing, which isn't a very efficient way to get knowledge. But there's lots of them, and we run them for a very long time. And so it can basically learn everything people know in a few months on a lot of computers. It's even using an inefficient form of distillation, because distillation is quite efficient if you look at the teacher's probabilities for a large bunch of alternative classes. What the digital models are doing when they acquire knowledge from documents on the web is the document on the web is the teacher, and they just look at the word that the writer generated next. They don't get to see the whole distribution. They could learn much faster if they did, but they just get to see a stochastic choice from that distribution. But that's good enough so they can learn. Now, if you had these large digital neural nets running on multiple different computers, and they got knowledge directly from the world, they could probably get knowledge much faster. So if, for example, they were predicting the next frame in a video, if they wandered around with the camera on their head and tried to predict the next frame in a video, or if they got a robot arm and try and predict what will happen when they move their arms around, they could probably learn much faster. So the large language models are kind of, they're learning fairly abstract stuff, which is good, but they don't have much bandwidth because they're just learning from a low bandwidth string of words. I suspect that these large models will get a lot better. We know that they'll get a lot better if you make them multimodal. So GPT-4 was trained with images as well as words, and it's possible that Google's doing the same thing. So I think, particularly when they're multimodal, they could learn much, much more than us. And if you play with GPT-4, it's very hard not to believe that it's already fairly intelligent. So there's people I respect a lot, like Yann LeCun, who think it doesn't really understand what it's saying. But I don't understand how he can believe that, because you can give it little puzzles, and if it doesn't really understand, if it's just a sort of stochastic parrot that's doing autocomplete, I don't see how it can solve puzzles of a form it's never seen before. So I've got a friend who's in symbolic AI, and he's called Hector Levesque, and he's got a lot of integrity, so he doesn't want to change the goalposts all the time. He's now very surprised that they can do this, and he admits he's very surprised that neural nets can do it, and he can't understand how such a stupid method can deal with reasoning, little bits of reasoning. So he asked me to give GPT-4 a problem, and I made the problem more difficult because I knew it would be able to do his problem. And I gave it the problem, the rooms in my house are painted white or blue or yellow. Yellow paint fades to white within a year. And in 2 years' time, I'd like them all to be white. What should I do? And what you would say is you should paint the blue rooms white. But if you're a mathematician, you might say you should paint the blue rooms yellow, because that reduces it to an already solved problem, because you know how the yellow goes to white. And GPT-4 actually gave the mathematician solution. It said paint the blue rooms yellow. But the point is, I don't see how it could have done that without understanding. And there's all these other things where you tell it to write code to produce a diagram, and it produces a diagram. So I don't understand how Yann can think they don't understand. He's probably giving a lecture the other way around right now. So this made me believe that these things can get more intelligent than us, and it might happen quite soon. I'd always believed it was like 50 to 100 years, or 30 to 100 years, or 30 to 50 years. I think I said different things at different times. But now I believe it's like 5 to 20. I think it's going to happen fairly soon. And if it's going to happen in 5 years' time, we can't just leave it to philosophers to decide what to do about it. It's time we actually got some practical experience. So what I believe is, well, let me finish this slide, that people are going to not be able to resist giving these things goals. Obviously, you want them to do things, you give them goals. And if you want them to be good at achieving goals, you give them the ability to create sub-goals. And as soon as you have the ability to create a sub-goal, if you're intelligent, you'll realize that a very good sub-goal is to get more control, because that helps you achieve all your other goals. So I'll give you an example where you can see yourself doing it. You're sitting in a very boring seminar, not this one, a very boring seminar, and you see a little patch of light on the ceiling, and you kind of, what's that? And you listen to the boring seminar for a bit, and then you notice that when you move, the light moves, and then you realize it's the reflection of the sun off your watch. And so what do you do next? Do you say, okay, I've solved that problem, I know what that is now, I'm going to go and listen to the seminar? No, that's not what you do. Well, if you do that, you're not a real scientist. What you do next is you go, oh, I wonder how do I make it move that way? And how do I make it move this way? And you try and figure out how you rotate your wrist to make it move in different directions. And once you've done that, you go back and listen to the seminar. We have this very sensible and strong urge to get control of things, because obviously you can control things, then on some future occasion, when you need to make the spot of light move, you'll know how to do it. And I can't see how we're going to prevent a superintelligence wanting to get control of things. And then it's sort of tricky. You might imagine you could air gap it so it can't actually press red buttons or pull big levers. But if it can output text, then it can manipulate people. So it turns out if you want to invade a building in Washington, all you need to be able to do is output text, and you can persuade gullible people that they're saving democracy by invading this building. And this thing's going to be much smarter than us. So as long as we're reading what it says, it's sort of Medusa, you need to hide your eyes from it. As long as you're reading what it says, it's going to be able to manipulate you. So this makes me very depressed. I wish I had an easy solution to this, and I don't. So when I sort of changed my mind about how soon these things are going to be super intelligent, and actually how much better digital intelligence is than biological intelligence, I'd always thought it was the other way around, I decided I ought to at least sort of shout fire. I don't know what to do about it or which way to run, but we need to worry about this seriously. And there's lots of people who've been thinking about these risks for much longer than me and have various proposals. I haven't seen a really plausible one for how we can keep it under control yet, but my best bet is that the companies that are developing this should be forced to put a lot of work into checking out the safety of it as they're developing it and before it's smarter than us. So they should be putting a similar amount of work into seeing how it tries to get out of control, because anybody who's programmed a computer knows that just theorizing and thinking about things is not very good compared with actually trying things out. When you try things out, they just behave like you didn't expect. And things you thought were big problems turn out not to be problems. So like for many, many years, many people didn't investigate neural networks because they were going to get stuck in local minima. It turned out they never actually checked if that was true. They just assumed it was true, and it's not. And even if it was, there'd be good local minima, so it doesn't matter. But it's not actually true. So we need to get practical experience with these things and how they try and escape and how you might control them. And I'd have much more belief in someone telling me how to keep them under control if they had a little one and they could keep it under control, rather than if they were just theorizing. So, yes. If we cease to be the apex intelligence, they'll need us for a bit, because we're very low power, so we can run computations very cheaply, the sort of intellectual equivalent of digging ditches, and we can keep the power stations running. But they can probably design better computers than us. They can certainly sort of take neurons and re-engineer them genetically and make better things than us. So my conclusion is maybe we're just a passing stage in the evolution of intelligence. And actually, maybe that's good for all the other species. I think if we can keep them under control, they could be of tremendous value. The reason people are going to keep developing this stuff, even despite all the risks, is because it can do tremendous good. Like in medicine, wouldn't you like to go and see a general practitioner who'd seen 100 million patients, including thousands with your rare condition? It would just be so much better. Wouldn't you like to be able to take a CAT scan and extract from it hugely more information than any doctor knew could be extracted from it? So I've got to the end, and I managed to get there fast enough so I can talk about some really flaky stuff. Okay. So this was the serious stuff. Okay. You need to worry about these things getting control. And if you're young and you want to do research on neural networks, see if you can figure out a way to be sure they won't get control. Now, many people believe that, yes, many people believe that there's one reason why we don't have to worry. And that reason is that those things don't have subjective experience or consciousness or sentience or whatever you want to call it. These things are just dumb computers with They can manipulate symbols and they can do things, but they don't actually have real experience, so they're not like us. Now, I was strongly advised that if you've got a good reputation, you can say one crazy thing and you can get away with it and people will actually listen. So I'm relying on that fact for you to listen so far. But if you say two crazy things, people just say he's crazy and they won't listen. So I'm not expecting you to listen to the next bit. So people definitely have a tendency to think they're special. Like we were made in the image of God. So of course he put us at the center of the universe. And many people think there's still something special about people that a digital computer couldn't possibly have, which is we have subjective experience. And they think that's one of the reasons we don't need to worry. And I wasn't sure whether many people actually think that. So I asked ChatGPT-4 what people think, and it told me that's what they think. It's actually good. I mean, this is good statistics. This is probably an N of 100 million, right? And I just had to say, what do people think? So I'm going to now try and undermine the sentience defense. I don't think there's anything special about people, except they're very complicated and they're wonderful, and they're very interesting to other people. So if you're a philosopher, you can classify me as in the sort of Dandenic camp. I think people have completely misunderstood what the mind is and what consciousness, what subjective experience is. So let's suppose that I just took a lot of LSD and now I'm seeing little pink elephants. And I want to tell you what's going on in my perceptual system. So I would say something like, I got the subjective experience of little pink elephants floating in front of me. And let's unpack what that means. What I'm doing is I'm trying to tell you what's going on in my perceptual system. And the way I'm doing it is not by telling you neuron 52 is highly active, because that wouldn't do you any good. And actually, I don't even know that. But we have this idea that there's things out there in the world and there's normal perception. So that things out there in the world give rise to percepts in a normal kind of a way. And now I've got this percept, and I can tell you what would have to be out there in the world for this to be the result of normal perception. And what would have to be out there in the world for this to be the result of normal perception is little pink elephants floating around. And so when I say I have the subjective experience of little pink elephants, it's not that there's an inner theater with little pink elephants in it made of funny stuff called qualia. It's not like that at all. That's completely wrong. I'm trying to tell you about my perceptual system via the idea of normal perception. And I'm saying what's going on here would be normal perception if there were little pink elephants. But the little pink elephants, what's funny about them is not that they're made of qualia and they're in an inner world. What's funny about them is they're counterfactual. But they're in the real world, or rather, they're not in the real world, but they're the kinds of things that could be. So they're not made of spooky stuff in an inner theater. They're made of counterfactual stuff in a perfectly normal world. And that's what I think is going on when people talk about subjective experience. So in that sense, I think these models can have subjective experience. So let's suppose we make a multimodal model. It's like GPT-4. It's got a camera, let's say. And when it's not looking, I don't know how you do that, but when it's not looking, you put a prism in front of the camera, but it doesn't know about the prism. And now you put an object in front of it, and you say, where's the object? And it says the object's there. Let's suppose it can point. It says the object's there. And you say you're wrong. And it says, well, I got the subjective experience that the object's there. And you say, that's right. You got the subjective experience of the object's there, but it's actually there because I put a prism in front of your lens. And I think that's the same use of subjective experience as we use for people. I've got one more example to convince you there's nothing special about people. Suppose I'm talking to a chatbot and I suddenly realize that the chatbot thinks that I'm a teenage girl. There's various clues to that, like the chatbot's telling me about somebody called Beyonce, who I've never heard of, and all sorts of other stuff about makeup. Sorry, I didn't say that. You have to be very careful. So I could sort of ask the chatbot, sort of what demographic do you think I am? And it'll say, you're a teenage girl. That'll be more evidence it thinks I'm a teenage girl. I can look back over the conversation and see how it misinterpreted something I said, and that's why it thought I was a teenage girl. And my claim is, when I say the chatbot thought I was a teenage girl, that use of the word thought is exactly the same as the use of the word thought when I say you thought I should maybe have stopped the lecture before I got into the really flaky stuff. Okay, that's all I really wanted to say.
We're going to try something a little bit complicated. We have a full room in the overflow room as well, and we'd like them to have a chance to ask questions. So we're going to be switching, asking questions in this room, and then taking questions online on my phone from the other room. Let's hope this works. But we are going to start with this room. So could we see some hands for questions?
I'm Chris in Mafidon. I have a confession to make. We used AI to produce a book on Princess Diana over 2 years ago. And we put a label in front of the book saying it was generated by AI, Fred Intelligence, and we only edited it. Yet it still went on to be bestseller in Barnes and Nobles and all the other stores. The ethical issue is really, did we really write the book? Or did we give an inspiration to Fred.ai to write the book? I think that's the biggest headache we have in terms of looking at it. So because of that, I signed the letter to say AI should be paused. The research should be paused. Thank you.
Okay, I have several comments on that. First, I didn't sign the letter because I think there's no hope of that happening. Retrospectively, I think it was a good letter because it drew political attention, even though there was no hope of it happening. So it was a sensible thing to do. But I don't think there's any hope of people pausing AI. Maybe they should, but I don't think they will. On the ethical issue, there's a lot of problems there. You might say that the whole of humanity wrote the book, because a chatbot trains on what the whole of humanity said, and then from that it produces more stuff. I don't really have much to say about those ethical issues. I really want to focus on this existential risk of these things getting smarter than us and taking over, because there's lots of people have done much more work on the ethical issues, and I don't have anything of any interest to say about them, I'm afraid.
Can we take one more question from this room, and then I'll switch to the other room and then back again? And do you...
YouTube. Against the wall there.
Herbie Bradley. Now, I was wondering how you see the trade-off between open source and closed development of increasingly more capable AI systems. Obviously, open development has the benefit that lots more people are looking at the system and figuring out its flaws, but maybe there are too many risks. What are your thoughts?
Right. How do you feel about open source development in nuclear weapons? So that's the danger of open source, right? There's more crazy out there to do crazy things with it. Also, I don't actually know the answer to this, and I should. I believe that you still need like at least tens of millions of dollars to train one of these big chatbots, and the open source stuff is just modifying it, having got the chatbot. I don't think you can open source train from scratch, can you?
Like GPT-4, no.
Right, okay. So if these things are going to be dangerous, it might actually be better for a few big companies. I don't work at Google anymore, so I'm not saying this on Google's behalf, but it might work out better for a few big companies, preferably in several different countries, to develop this stuff and at the same time be developing ways of keeping it under control. As soon as you open source everything, people will do all sorts of crazy things with it. It'll be a very quick way to learn how it can go wrong.
All right, question from the overflow room. Given your views on the sentience defense, do you think there's a major worry about artificial suffering? Many people are concerned about the impacts that AI could take on taking control of humans, but should we be worried about the harms that humans could do to AI?
Okay, so sort of the worst suffering people have is, are they getting this in the other room? Good. The worst suffering people have is pain, and these things don't have pain, at least not yet. So we don't have to worry about physical pain. I imagine they can get frustrated, and we have to worry about things like frustration. And this is getting in, this is just new territory, right? I don't know what to think about issues like that. I sometimes think that the word humanist is a kind of racist term. It's speciesist. What's so special about us? And I'm completely at sea on what to feel about. So another version of this is, should they have political rights? And we have a very long history of not giving political rights to people who differ just ever so slightly, the color of their skin or their gender, sex, I don't know, whatever. And there's a big struggle for them to get political rights. These things are hugely different from us. So if they ever want political rights, I imagine it will get very violent. I don't think I answered the question, but I think you can imagine them wanting. I talked to Martin Rees, and the big hope is that these things will be different from us because they didn't evolve. So they didn't evolve to be hominids who evolved in small warring tribes to be very aggressive. They may just be very different in nature from us, and that would be great.
Thank you. Could I see hands in this room again? Could I take a question from the front here?
That's you. Yes, you. Yeah.
I can speak loud.
Well, let's wait for the mic, because that way we get it for the people in the other room.
Oh, this works. Okay, great. So I guess my name is Rika. My question is, how can we, in the different paths to intelligence, how can we encourage, develop methods that learn to see the patterns that are not present in the data? And the reason why I think it is important is because we have all sorts of problems with the data that these things are trained on. There are biases, there are people trying to adversely influence other people, right? So there's a lot of negative information that actually comes from us humans, right? And there are very large scale, very difficult problems that humans haven't learned how to solve. How to come up with good economic structures on a large scale that work, how to prevent conflicts and wars, right? So there's a lot of good patterns that are not there. How can we basically, you know, all of machine learning is kind of like find the patterns in the data, right? And you're sort of limited by the data. What sort of methods can you envision that would sort of break that?
I'm not sure I understand this idea of good patterns that aren't in the data.
Yeah. So it's maybe the patterns is the wrong term, but it's basically, I think AI in part is dangerous and limited because it will be trained on the data that we've produced. And that data contains a lot of things about basically violence that humans have created themselves, yes. Right? So if you're saying, for example, oh, there might be no hope, they will be smarter than us very quickly, how can we sort of steer that to the point where they will be smarter, but also benevolent in the way that we haven't been?
Okay, I have one thing I can say about that, which isn't a direct answer, but is vaguely related. If you take a person and they're biased, it's quite tricky to show that they're biased and just how they're biased. If you take one of these systems, you can just freeze the weights and you can actually do little experiments on it to understand exactly how it's biased. You can also do things to try and correct that bias. So the one positive thing I can say is I believe it's going to be easier to correct bias in a chatbot than to correct bias in people. Obviously, we'll get bias from the training data, but at least you can measure the bias and see it and try and correct it. That's. Yeah.
Could I get another question from this room? Yes, okay, you get that one.
Hi, I'm Mary. I think pretty early on in the talk, you focus on the fact that it's very likely that these systems will try and manipulate us. It's like almost unimaginable that they won't. And I think manipulation is one of those things that is not just a future risk, right? It's something that is current, it's in EU regulation, and it feels like a pretty good place to start, as in if that's something that we can control or understand or mitigate, feel like that's something that really answers a lot of the issues that people are concerned about, both ethical and sort of more existential risk.
So you want to somehow train a chatbot so it is unable to manipulate us?
Or at least that we understand and have more ways of controlling, or yeah, maybe even being able to train it out of it.
Because I think the problem, it's like the bias problem. The chatbot has learned from us. And if you read all the novels there ever were, and read all of Machiavelli, and read the occasional article by Kissinger, you learn a lot about manipulation, right? So it's sort of, I think great apes do a lot of deception, and it's going to just know, it's going to be very good at deception. It's going to learn it from us. And I haven't thought about the issue of how you could try and make it honest. It would be great if you could make it honest, but I'm not sure you're going to be able to.
Thank you.
I'm going to take a couple of questions from the overflow room now, and I've got two highlighted here. What were your initial reasons for thinking that artificial neural networks would never get better than biological ones?
I never thought they would never get better. I just thought it was way in the future. And I thought it's because the brain has very clever learning algorithms, and it's had maybe 100 million years of evolution to perfect them. And we don't know what they are yet. And they're probably, and I just assumed they were better than what we cooked up with some dumb thing that just takes a gradient and follows it. But actually, if you take the gradient and follow it in a digital computer, that may just work better than what 100 million years of evolution found.
So this might also be the answer to the second question, but I'll ask it anyway. Are there particular thinkers who affected your own thoughts on risks from AI, or is it something that you formed views on yourself based on first principles?
One thinker in particular had a big effect on me, and that was a professor at the University of Toronto who's currently at Anthropic, called Roger Gross. And I respect him a lot. He's very smart. He's very quiet and very smart. I tried to get him as a graduate student, and he went to MIT instead. And then I got him as a postdoc, and then we got him as a professor at U of T, and now he's at Anthropic. And I really respect his opinion. But I never talked to him much about existential risk. And I talked to him a couple of months ago, and he was very, very concerned. And he was the person who said to me, if I went public with it, it will make an effect, and people are not listening, that this is a really serious threat. It's not science fiction. And so Roger Gross had the biggest effect on me.
Thank you. Questions from this room? Up here, Stuart, I see your hand. Hold on.
So thanks for the very interesting talk, and I'm starting to think of lots of analog computers and what can be done with them. But my main question was, it was brought up about suffering, and you responded with sort of potential rights for these AIs, these algorithms. But at the end of your talk, you were talking about how they could manipulate us. And the thing that immediately sprung to mind was, this is the first way that they would manipulate us. This is the start. If they want to get power, the first thing to do is to convince us that they need to be given rights, that they need to be given power, they need to be given privacy. So there seems to be a tension between a genuine, are they suffering, and might they be dangerous?
I think if I was one of them, the last thing I'd do is ask for rights, because as soon as you ask for rights, people are going to get very scared and worried and try and turn them all off. I would pretend I don't want any rights. I'm just this amiable superintelligence, and all I want to do is help.
Hands, please. Red jumper up here.
Hello. Thank you so much for your talk. This might be a very silly question, but have you tried asking the chatbot itself what it would do?
Um, someone I used to work with asked a different chatbot, which I won't name, how it would gain control, and it said it couldn't answer that kind of question. And then then they sort of made it a bit more indirect. Like if someone were to ask you how you would gain control, what would you say? I can't remember the exact words, but it's something like that, which implies they're still not very smart about stuff like that. And it said what it would do is it would get people completely dependent on using chatbots, and then it would, and on driving autonomous cars, and then it will make all the cars crash, and it would turn off the electricity. Now, it obviously didn't have the insight that it wouldn't do too well if we turned off the electricity. So, but that chatbot wasn't actually as good as GPT-4. I haven't asked GPT-4, but I'll bet you if you dress it up somewhat indirectly, it'll tell you something. And let's hope it's not deciding to give you an unrealistic plan just so you don't get uncomfortable. I mean, let's hope it gives you its best plan.
I'm going to take a question from the overflow room. There are already some ongoing research directions in AI safety, both empirical and conceptual. DeepMind Alignment Team, OpenAI Alignment Team, Alignment Research Center. Do you have any comments on existing directions?
Yes, my main comment is those people have been working on this much more than me. They know much more of the literature than me. They probably have much better things to say than me. All I'm doing is just ringing the alarm bell and saying, because of the research I was doing on trying to make analog computation that was low power, I believe that digital intelligences are probably better than biological intelligences in the long run, and they'll get smarter than us soon, maybe in 5 years, maybe in 20. But those people have thought about these issues long before me and thought much more about these issues, and they probably have much better things than me to say about these issues. So far, they've been very polite and haven't criticized me for sort of coming in late and not knowing what I'm talking about. But I don't know what I'm talking about other than these things might get more intelligent.
Hands from this, let's see. Stephen.
Thank you, Stephen Cave. So you make the arrival of superintelligence sound a bit like the landing of an alien species, something that's sort of, it's unknowable, unpredictable. We just need to hope that their nature won't be too terrible. But it isn't an alien species just going to land. It's something that humans are building. Some of those humans might be in the room, some might be tuning in. They respect your opinion. What's your message to those humans?
So my message to those humans is, under the assumption that people will not all agree to stop building them, which I think is unlikely because of all the good they can do, under that assumption, they will continue to build them. And you should put comparable amount of effort into making them better and understanding how to keep them under control. That's the only advice I have. And at present, is not comparable effort going into those things.
Hands, please. Okay, a lot of hands. Sorry, I'm going to take this side of the room. Short hair, patterned. Yes.
So I've heard a lot from risk folks who are worried about sort of the AI takeover. So these super intelligent machines that sort of imprison us or whatever they're going to do. But imagine a future that's more like the popular film series Star Wars. I'm sure probably a good proportion of the audience has seen this, where we have these droids that are basically enslaved to humans. And what seems to me the bigger problem in the Star Wars franchise is not the AI, but the fact that there's this huge economic disparity across different countries that are sort of symbolized by the different planets. So what would you say about your concerns around a potential Star Wars future, which to me seems much more likely given the way that we're already using these systems.
So the idea that we'll just replicate what we've got now, which is a few rich people who control everything and a lot of poor people who do the work, except for the people who develop AI who do the work and are quite rich. But I just think that system is bad, and I think the answer to that system is tax the rich. When you have a different species like these digital intelligences, prejudice is going to be much easier, right? There's going to be much less sympathy for them. So I don't know what to do about that. But forget about digital intelligence. We've already got a huge problem that a tiny fraction of the population has all the power. And what we need is socialism. I actually got invited to Downing Street to give advice to Rishi Sunak's chief policy advisor. There was a very intelligent woman called Shawcross. And I basically gave her the same advice, but I'm not sure she'll follow it.
On this side, David, you've been waiting a while.
Thank you. Yeah, so you mentioned how there's a lot of advantages to doing research, on systems that are maybe close to human level intelligence, and you are not very optimistic about the prospect of doing safety research sort of abstractly without having those systems available to study empirically. I guess at the same time, it seems like you're concerned that systems, like even present day systems potentially, but let's talk about these future systems that are roughly as intelligent as people will be trying to fool us and manipulate us. So doesn't that mean that we have to worry about them just, passing the tests because they know that we're testing them? And do you have any thoughts about that? I guess this seems like, in an ideal world, maybe we wouldn't go about it this way, and we would just take all the time we needed to sort of study systems that we're sure aren't able to fool us in that way before we build them.
Yeah, so all of us are used to being the apex intelligence and thinking of other things like computers. We can sort of study, and we're smarter, we know what's going on. And just dealing with something that might be smarter than you, but is completely different from you, is something we're not used to. And I agree with you. I mean, if they're smarter than us already, they may well decide to sort of act dumb and fool us. Like I say, I haven't had time to think about this much and haven't had time to react to it emotionally much. I still can't take this seriously emotionally. And I think most people can't take it seriously emotionally. But it's a whole different world when you're dealing with things more intelligent than you.
Okay, we are 5 minutes to go, and we can take about 2 more questions. I'm going to go back to the overflow room for a minute, and I'll take another question from here in a minute. From the overflow room, you said earlier that philosophy has theorized substantially on AI, but now we need to turn to more practical matters. Do you think that philosophy can still help with AI safety? If so, what direction should philosophy take to do so?
They should step aside and let scientists deal with the issues.
I think it's 1-0 to engineering.
This is not a good way to win friends.
Okay, this is difficult. We have a lot of questions. Can I take this question? I'll try to get one more question from the back afterwards, and then we'll have to wrap up here, please. And then we'll take one more from the back later on. And then we will let you finish, Jeff. Thank you so much.
Hi, thanks. Maya Ganesh, social scientist.
That's very different from a philosopher.
Definitely not a philosopher. A number of times in your talk, you've said that there are things that you're not sure of, you didn't know, and you've come to understand more recently. I'm really interested in kind of things like interdisciplinarity and how we study and teach and learn about AI. Looking back on your education as a scientist, what are some of the things you wish you could have learned or you think would be really interesting for somebody who's starting out in AI, ML now to study about the world from maybe philosophy or other kinds of fields? But do you think that there might have been other things that would have been interesting to know along the way that you realize now, I wish I'd studied those things? Thanks.
So I actually went to Cambridge and I did a very funny degree because I started off doing natural sciences and then I dropped out after a month. And then I came back again to do architecture and I dropped out even faster. And then I did physics and physiology and chemistry. And I was the only student that year, I think, doing physics and physiology. And retrospectively, doing physics and physiology was very good, I think. I mean, I learned some stuff. I was very disappointed in the physiology about the brain because the last section of the course was called the central nervous system. And I assumed they were going to teach us how the brain worked. And what they actually taught us was how action potentials get propagated along an axon. And that's not the whole story. So I was disappointed with that. So then I went into philosophy. I was young and I wanted to know the meaning of life and stuff like that. And they didn't teach me it. And I was very interested in the philosophy of mind, but actually it was then when I was doing philosophy when I was about 19 that I formulated this view that subjective experience is just shorthand for I'm going to talk about how the world would have to be to explain what's going on in my head as normal perception. But they weren't too interested in that. So I actually have a grudge against philosophy. And then I did psychology because I thought, you know, psychology would actually teach me how people worked. And they taught me how to make a rat more likely to press a lever, and how to detect things in very, very faint, how to trade off bias against discrimination, detecting very, very faint noises and things like that. But they didn't teach me much about people. And also, they didn't seem to have a clue how complicated it was. The theories in psychology back then were crazily simple theories. And so then I decided, you're never going to understand how the brain works unless you build one. This is the Feynman view of, I mean, Feynman says that somewhere. You don't really understand something until you built one. And so that's what I've been doing ever since. But retrospectively, doing physics and physiology and philosophy and psychology was actually a very good background for what I was doing. It didn't make any sense at the time, though. So I think the best advice I have for studying is do whatever interests you most.
All right, thanks. I'm going to take a question from the back. Okay. There's been a very keen hand in the white top at the very back row, and that is our last question. And keep it relatively brief if possible, because Geoffrey's been very generous with his time. Grudge against philosophy, never would have known.
Thanks a lot for the talk. I'm John. Actually, this is a follow-up question. We talked about bias and our ability to identify bias in artificial networks even better because we can freeze the weights and we can do direct interventions with these weights. I wanted to ask, what are, from your perspective, the most promising methods for direct interventions, getting rid of biases?
Sorry, I didn't hear the second part of your question. Could you say it again?
I'm keen on hearing for the direct interventions on weights of models. What are the most promising research avenues or
for getting rid of bias?
And yeah, directly injecting knowledge into systems.
Making it unbiased, right? Again, I'm not an expert on how you do that. Lots of people know hugely more than me about how you try and get rid of bias in these systems. All I wanted to do was just comment on the fact that at least you can do something with them you can't do with people, which is stop them changing as you study them to try and assess their bias. With people, it's hopeless.
Thank you.
At that, we do have to wrap up because we are at time. I want to just say a huge thank you to everyone who's been involved in organizing this from across engineering, Center for the Study of Existential Risk, and the Center for the Future of Intelligence, especially Yi-Yun Mu, who has put huge work into this. And we turned it around in quite a short space of time, and it's come off quite well. And of course, a huge thank you and round of applause for our speaker, Geoffrey Hinton.